Good morning, everyone. So I'm Rafa. I think by now all of you have met me in some capacity. So I have these 3 hours to try to give you an introduction to elasticity of horizontal axis wind turbines. So you know the setting I put together here. So I have 2 computers with me. On one I will be running through slides, and I have a pen to annotate. And then the computer I'm using to talk, I have the chat. Actually, I forgot. I have the chat online next to a copy of the slides and the video feed. So I do welcome you guys. I will deny anyone access request for control. If you try to get control of the slides, that's not that one thing I will do. But if you want to ask questions, do please write messages there or raise your hand. I should be able to respond quickly. The talk I'm putting today is definitely not as well structured as the one you got on Friday. I haven't written a book on this, so I was trying to put key information I thought would be interesting for you to have some awareness of what's going on in wind turbine technology, and particular elasticity. That means as I switch through topics, you have plenty of time or events in which you can ask questions. So just to say about me, and this is the bias I'm putting into this talk. I work in computational methods in aeroelasticity for many years, and both Andy and myself, we are in aerospace department, which that means we bring a bias to this, which we come from an aerospace aircraft sort of application environment, and we are indeed translating much of the technology that we see in there into wind energy applications. If you need to, I think it's an obvious thing to say, but if you ask me why I'm working on wind energy, I will basically answer through I have a dual answer here. The first is what I put on the very first slide here. If this goes through, let me see. There you go. This is a picture taken in Greenland sometime in May last year. At that time, this time of the year, typically this is a huge ice shelf or ice lake. When these guys were going to do their year trip, this is some sort of guards that live in Greenland. They found that the whole thing was full of water. So we have a huge challenge as mankind, which is dealing with climate change. And a key element of the response is renewable alternative energies, so energies that don't really rely on fossil fuels. Wind energy have taken the lead on that, and I could put plenty of charts. I'm pretty sure you're all aware of this, of how wind energy is taking over huge chunks of the energy produced, how electrification relies on the ability to harvest energy from renewable sources, and how luckily the cost of wind energy has dropped quite substantially over the last decade, to the extent that actually it's very competitive. Having said that, it is not by all means an easy problem. It's not a mature technology. It's not something for which we have all the answers. And that goes to the second reason I myself work on this. I'm clicking on the wrong computer. That's the one thing I need to get used. This is a picture of a wind farm on a day in which the moisture in the atmosphere was about right. So you could actually trace the wakes of each individual wind turbine. This is a very famous picture in the wind energy community. Now, what this thing is showing is that the aerodynamic environment around wind turbines is anything but nice. As a matter of fact, having come myself here from an aircraft sort of environment, this is way harder aerodynamically than anything I've seen on aircraft flows. It's a really challenging sort of situation to consider. And indeed, this is one of the key elements, how you get optimal performance out of a farm which need to operate in these conditions. This is not something you can really do much about. The fact that there are wakes behind wind turbines, and the fact that you need to cluster them because otherwise they will be uneconomical. So there are massive challenges in terms of actually doing prediction, doing having a proper understanding of the full physics that occur in these environments. So, having said this, what is that I would like to cover today? Well, I make first a very quick intro to some basic definitions on wind energy, just explaining how a wind turbine works. And then I will run through via conventional or a standard way of splitting problems in elasticity. I will start with static problems in elasticity, which for the point of view of wind turbines effectively is linked to the performance that we expect to see on the systems. Then we'll go into dynamics, which basically in terms of wind turbines applications has an effect on the loading on the wind turbines as well as the fatigue that you would expect to see on the systems. And finally, I will have a few things to say about the control aspects on elasticity, which typically is referred to as aeroelasticity. And as I say, I keep monitoring the chat, so do please interrupt me at any time if you have any questions to ask. So, okay, that would be the very first thing to show. What is the wind energy a wind turbine doing? Well, a wind turbine basically is extracting energy from a flow. Okay, that's what you would expect the wind turbine to do. So this is the classical cartoon that you get to see in these cases. This is what I'm showing here on the left. So what we have is some wind coming upstream at some velocity. Then somewhere we have our wind turbine, which typically looks like that. And then the wind turbine, what it will be doing is effectively slowing the flow. You slow the flow, you extract momentum out of it. That momentum you put it into a converter. That generator generates electricity. You get a cable out. You get electricity power out of the wind turbine. In terms of the fluid mechanics of the problem, which this is doing is opening what we would refer to as stream tube. You consider a particle of air which is going down from infinity upstream of the wind turbine. That will reach the wind turbine, and as it reaches the wind turbine, it will open such that the area times the velocity is equal to the area, let's call it 2, is equal to the area 1 times the velocity 1. So one feature you will see, and this is very easy to observe on this previous picture, I have this cartoon of the farm, is the wing wakes, rotor wakes, they open compared to the size of the rotor itself. In that process, then there's extraction of energy. That extraction of energy goes into a converter. The converter goes into a generator. Generators are typically installed on the nacelle. And for very large wind turbines, getting an idea of size is important. So a very large wind turbine typically has a tip to bottom height of about 150 to 200 meters right now, the largest ones, very, very large. Rotors which are approaching about 100 meters in terms of dimensions. And nacelles, which is where you put these, all the gearbox and most of the energy transformation systems of the order of several hundred tons. Okay, these are massive constructions. So having come to this myself from an aircraft universe, the scale is actually larger. And an implication of that is that much of the design aspects actually are coming not from aerospace engineering, but from civil engineering. So it's very often that you get to see these systems as civil engineering structures. Okay, very much heavy, stiff sort of designs, all the way to the gearbox. And then the aerospace engineers take over on the rotor sort of thing, which are the moving parts of the system. Now, locally, if you look at any of the airfoils, of course, those are wings, which basically are generating the thrust through transforming the flow into lift. It's lift-driven devices. That's much more efficient than drag, as you would expect. Then what you will have is that locally, the sections of the wind turbine, and this is what I'm putting on the plot here, what they will see is a flow that has two fundamental components. One is the incoming flow velocity, U infinity, which I put on the left, is here on the right as well. But the second one is the fact that actually it spins and it spins relatively fast. So that's what I refer here as omega r. Okay. The combination of these two velocities defines the relative velocity between the rotor at a particular section of the rotor. R is the radius, so as you go along the rotor, you have different speeds. and the incoming flow velocity. The combination of these two generates an effective wind velocity vector. That's how the airfoil sees the air coming. And therefore, there will be an angle of attack, which is how this vector is oriented with respect to the rotor. And each rotor will be aligned, or each rotor section will be aligned with the incoming flow, such that this angle of attack becomes maximum performance in terms of how much thrust you can get for the particular section. All right. So having said this, the key magnitude that we care about when we're looking at the wind turbine is referred to as a power curve. What this is saying is how much energy, how much power we can extract from a wind turbine as we run through different wind velocity speeds. Assumption here is that you are always aligned exactly with the wind speed vector, which is never exactly true, but roughly wind turbines can align themselves to the dominant wind direction at any given time of the day. And then in any wind turbine, what you will see is that there is a minimum speed. That's the startup speed down here. This is for a very small wind turbine. 250 kilowatts is really tiny, but that's an example of a wind turbine. This is a wind turbine which starts operating at 3.5 meters a second. Below that, it doesn't start. Wind turbines need to be self-started, which means they have to move from still conditions to operating conditions by themselves. And that's a non-trivial design problem because you have separation at very low speeds. You need to make sure that that separation generates enough force for the wind turbine to start spinning and reach its nominal rotational velocity. Then as the wind turbine increases, of course, the wind power increases, and that's this part of the curve. Then every wind turbine is designed what is said as a rated wind speed. That's the wind speed for which we are calling that the nominal condition. This is a combination of choice of wind turbine parameters as well as the wind setup at the condition in which the wind turbine is put on the particular farm. So you want that number to be as high as possible, of course, but that depends on the available wind that you may have. So typical number is about that, I saw there, about 14, 15 meters a second. And then above that speed, wind turbines are tapered in terms of the amount of power that they get. And this is by design choice, okay? So these, if you keep increasing the speed, you could technically, potentially, you could increase that graph to the top. But there is a engineering choice there, which is it becomes increasingly harder to make a wind turbine that is able to sustain that wind speed and achieve maximum power. They will have huge amounts of loading and they would become very massive. So there's a design constraint there, which effectively is what is referred to this fixing this rated power. So wind turbines are designed for rated power, and the expectation is that they operate on this regime for most of their life. Now, wind can get very strong, and wind gets strong enough, you end at a point which is called the cutout speed, beyond which the wind turbine actually is stopped. It's unsafe to keep performing. Of course, this is something you wouldn't like to see, but the reality is that you need to put limits to any design, otherwise it will be unfeasible. What I put here in this cartoon on the right is the nacelle of the largest wind turbine I know of, which is a GE, it's called Haliade X. It's about, if I recall, 12 gigabytes of power. This nacelle is sticking at on top of a mast which is about 150 meters tall, and it weighs 500 tons. Okay, the scales become really crazy on these very large wind turbines. Okay, that's on what to expect from a wind turbine. Now, how they are evolving, and this is what drives in a small part research, they're evolving in two directions. One is we see an increasing need for wind turbine in offshore environments because that's where we have the most available power. So wind is stronger if you go to middle of the ocean, and you have plenty of space. So of course it's much harder to keep putting wind farms on land. So what there has been a trend towards offshore farms for the last few years, and the UK, as you know, is one of the leading countries on that because we have plenty of, it's an island, we have plenty of sea and plenty of wind on that sea. But what that means is that we are also moving into an environment in which the wind turbines are no longer just clamped on the base. This is the classical wind turbines when you go to either on land or very near offshore. They have monopile wind turbines. Now you go into different sort of substructure systems to the point where wind turbines in the middle of the ocean now are on floating structures. This is the current kind of massive technology challenge, how you make these things to be efficient or economical. Issues there is, well, let me put the second cartoon together on this one. The second trend which is happening simultaneously is this plot I have on the right. This is the size of wind turbines with time. This is the current largest wind turbine is that one I told you about, the GE wind turbine. There's a similar one coming from Siemens. This typically is about 200 meters, 250 meters, as you see down here in terms of dimensions. And in comparison, this is a Boeing 747 put together on the same scale. And these are wind turbines which are already operational. 10 megawatts are right now being installed in the North Sea in Scotland. Now, what are the challenges? Well, there are many challenges from the point of view of even how you actually install a wind turbine this size in the middle of the ocean. This is a no means task, no trivial task. But from the point of view of what I'm discussing today is you have very, very long blades. By definition, they will be flexible. You would expect that to happen, as well as the tower. So you have flexible blades and tower. And that means, as we will see in a minute, that's aeroelasticity, structures and aerodynamics interacting. But when we go offshore, we have a second issue, which is this is also on a floating base. And that means we have a third element on the equation, which is the presence of waves and underwater currents, which also generate loading and also generate interaction with the structure, either the one underwater or the one which is sticking on top. So all this together makes for very nice challenges from the point of view of modeling, design, and control of these funds for stabilization, as many of you are aware of. I'm talking about flexibility. This is just a couple of pictures I took from wind turbines and their high load conditions. Santano, yes? You're raising your hand. Unmute yourself. No? I see Santano with a hand off. You raise your hand, I will stop, but of course I expect you guys to unmute yourself. Otherwise nothing happens. Nope? Okay. Continue. If you manage to get your microphone going, just let me know. What you see here is a snapshot of Siemens blade under high wind, and this thing that you see here is indeed how much the wind is, the blade is deforming as it goes. Yes? Yeah, but take out yours, otherwise it's take out this. Hello.
No, ask your question now and then.
Yeah.
Yeah, you can talk.
Hi.
Hello.
Hi. I'm sorry. I didn't mean to interrupt, but my microphone is not working. I just wanted to ask you the speed, wind speed limits, and the size of the windmill, the wind tower and the wind blades. There must be a relationship between them as well, right? Like, because you said after 13 to 15 meter per second, then you put a limit on the rotation and on the velocity.
Okay. The wind, so the wind speed depends on the location. Okay, so there's so much wind you can have available. So these sort of things are fixed. However, as you go higher in the atmosphere, the wind speed is faster. Okay, so wind turbines are all by definition on the boundary layer of the atmosphere. A boundary layer is a situation in which the wind speeds are decreasing. So why wind turbines get taller in one way is because the taller you are, the faster the winds to some level. Okay, and typically the atmospheric boundary layer is about 400 to 500 meters. So we are not quite there yet. So there's still growth potential there. The second reason they get larger is because the power, of course, goes with the area, but also goes with the spin, with the wind spin. So the larger the wind turbine, the more power you get out of it. But then, of course, the larger the wind turbines, they are designed to sustain larger forces in general. So you would expect the cutout to actually move to the right and the velocities to move to the right as the wind turbines are larger by definition. All these are happening.
Okay. Thank you.
Yeah, Borjan?
Yeah, so I also have a question, a very simple one. So I want to know what is the real reason for requiring flexible blades? Does this increase the stability of the wind turbines or the performance?
No, there is no good reason for it. If you talk a civil engineer, which are involved in this, they keep asking why they need. The reason is they're 100 meters long. Okay.
I mean, intuitively, you would expect that the fact you have flexibility, it is going to increase the stability when the loads, for example, the fluid is very quick, right? I mean, this is what I would expect.
Not necessarily, because things average very quickly. So they have an effect on damping forces. But the main reason is structural. Okay, the reason they are flexible is because you can make a 100 meters longer structure which moves. You stick it on top of a wind turbine, you rotate, and you need to make it economical. So you need to deal with flexibility. It's impossible not to deal with. The second is you would expect that things scale linearly. So you have a larger wind turbine, therefore you have a same amount of flexibility just over a larger area. The actual truth there is no. If you scale the weight of wind turbines with the power, that doesn't go linearly. Okay, so as wind turbines become larger, things don't scale as nicely. And that means you need to start putting constraints somewhere else. And one of them is the reducing weight of mass on the blades. Okay. So it's not something you like to see, but it's something you have to deal with and live with. And every structure is always flexible. And these ones, by the sheer size of them, it's impossible not to expect them to be flexible. Of course, that opens opportunities. And that's exactly the sort of things we're working in my lab and many other places. So once you have a system which is basically have more degrees of freedom, you have the ability to use those for potential good benefits, so to your advantage. And that's the sort of things we're looking at. And one of them is you might look for stability. You might look for those to increase performance at very high winds. You let them deform in the right way. So what I will talk at the end is called aeroelastic tailoring. When they deform such that actually you dump loading. Therefore, you can keep increasing velocity. So there are features that you can embed once you have the ability to actually design a system with flexibility. But the short answer is you rather wouldn't have it if you could avoid it.
I see.
Okay.
Thank you.
But can I just ask a question on this?
Absolutely. Yeah.
About
I want you guys to learn answer the wind turbines. I'm really pleased to see this question now, as opposed to me just giving you an hour talk on
Nice.
Yeah, please.
Because about flexibility, I do remember instead that when I was in Airbus, I was working there, and they were instead looking for wings to be flexible in their case. Yeah. But maybe that was if I remember correctly, but I'm not aerospace engineering, they wanted to minimize the load on the structure. That's why they wanted to look for flexible wings. So wouldn't this be an advantage for the wind turbine that somehow, okay, if it's stiff, maybe you can maximize the energy that you produce, but if it's flexible, somehow you take out weight from the structure. So from the design phase, it's better, no?
Exactly. I mean, and those things are the side effects. So flexible means lighter. Lighter means if you are the guy which is installing it, you'll be happier because you have a crane which is half the size. Okay. Yeah. So exactly. there are all these collateral effects which are positive out of it. Absolutely. But there is no. The key on this is that from an aerodynamic point of view, there is no fundamental advantage of these things to be flexible. It's just a complexity. And at the end, these are aerodynamic-driven devices. So what you would like to see is a shape which is optimal. That's optimal aerodynamic kind of design. But of course, that shape would change as the conditions change. So you need to adapt with that. Sure. It's a very rich problem. I mean, that's why I work on this. It's a great problem to work on. Okay. I have a couple more examples on that as we go down. So let me introduce aeroelasticity for a start, okay? Because I've been saying this, but not everyone may know what I'm referring to. So this is the classical way in which aeroelasticity is presented. So basically, we're talking about problems in mechanics in which we have systems which are driven by the combination of the interactions between inertia, elasticity, aerodynamics, and control. And the way I like to present this is the following. So we can take a mass m, okay? We'll have inertia. And you know the dynamics of these are going to be driven by Newton's law. You put a force on this, it will move according to a mass given an acceleration. Now, of course, you can make the mass to be held by a spring. In that case, what you have is a system in which you have interactions between elasticity and inertia in the most simplest way. 1 degree of freedom system. As you know, you just excite this system, you have conservation of energy between inertia and elastic effects, you have vibrations, you have some richness of behavior that comes out of this. Now, I can take this and I can make this now an airfoil, okay? And I can put this airfoil on a current. It's the same mass, it's the same stiffness, but now this will have an additional set of forces which come from the fact that this has an aerodynamic shape. And if I put in a flow, I will have the same system with inertia, elasticity, and aerodynamics interfacing. Now, in that case, depending on what's coming on the flow, these will have vibrations which I may or may not like. It will have stabilities or instabilities associated to the interaction between these 3 degrees of freedom. It's no longer so trivial what will happen here. So what I might want to do is to actually add a control surface. I define my actuator into this. And in aerodynamics, the natural way of acting is through control surface deflection, which is a way to modify the flow by just moving a small part of the aerodynamic body. And then we have the control elements. So aeroelasticity, in an essence, is dealing with systems in which all these elements are interacting with each other. The forces rely on the presence of springs, which is the deformation you have, and the presence of a flow, which defines the aerodynamic forces. The control will need to deal with all those simultaneously in some ways. And the various interactions between all those elements define the sub-problems I'm going to be discussing today. So the first one I have here is what we refer to as static aeroelasticity. This is simply equilibrium conditions we have between aerodynamics and structural forces. This is how much it deforms to sustain the forces without having any dynamic effects on the process. If things move, we end up in the area of vibrations when you have floating systems, on the floating systems which are moving and interacting with flows. If we are considering the 3 elements together, we end up something called dynamic aeroelasticity. And when we put the control, we refer to this as aero-servoelasticity. And one of my favorite movies ever is, if you haven't seen this, is a solar power aircraft taking off. This is a 80-meter long structure which is deforming, is interacting with the flow, it has control surfaces to take off, and is the ultimate aero-servoelastic system. And by the way, massively nonlinear. It's changing shape instantaneously and it flies. And it also crashed because it's very hard to get right. This is a 2001 and this plane crashed in 2003. It was an experimental plane by NASA. So let me see. This is what I was discussing about before. Aeroelasticity is you can see it as basically it's design effectively. It's the ability to have trade-offs between competing interests. So, and again, I'm bringing my aerospace background here, but I think it's more intuitive to see here things in that context. If you were to design an aircraft from the point of view of an aerodynamicist, it will most likely look like this. They don't care about the ability or the need to take people on board. They will just fly a wing, which is the most efficient way to get around. If you were to design an aircraft from the point of view of a structured person, they will make everything out of beams, which are very to assemble and put together, and they will never break. If you were to define the aircraft from the point of view of a manufacturing, you will just make a box with cardboard probably and hit it with nails, so you can make it in 5 minutes. And that answers probably the questions I had before. So a wind turbine will need to find compromises between all of this, but out of those also come opportunities, which is the fact that now that you know that you have to deal with flexibility, maybe there are things that you can get in the performance which will benefit from it. From a control point of view, I like to see our elasticity as a feedback exercise. So you have 2 systems which interact. You have the aerodynamics, which basically generate forces on the structure. Those forces deform the structure, and then those displacements feed back into the aerodynamic part of the problem. And indeed, the performance of the system is a coupled system sort of situation. The stability of the system is going to be depending not on the individual stability of the subsystems. its own life by itself. When you put it together with a control system, what we have is yet another feedback loop interacting with these three in different combinations depending on where the control system is acting. But in general, you will just put a huge block on the aeroelastic system and then another feedback, which is what you design the controller. And then you need to deal with the situation I'm referring on here, which is how you manipulate the performance of that system on top with a control system which may need to adapt as the wind speed keeps adapting. How is aeroelasticity typically introduced? I want to spend some time on this because it's the classical way to present aeroelasticity and is the most intuitive one I found as well to get an insight of what's going on in the problem. So consider this thing on the right is my wind turbine blade sticking some nacelle, and then I go around my 100 meters long span. I look at a certain section, Y, and there typically what I will have is these being affected by mostly bending forces, which I'm trying to pull it out, and torsional forces, which I'm trying to twist it. You could try to address this problem on the full blade, and indeed that's what we do routinely for analysis. But to understand the basic physics, you can generate a canonical problem or a canonical model of this with 2 degrees of freedom. You take an airfoil, which will have the aerodynamic features, you attach it on springs, and now you let this airfoil to move on the vertical axis, which will correspond to the vertical bending, or to rotate, and that will correspond to the torsional displacements. And we refer to this the typical section problem. And then when you write the typical section problem, basically what you have is a basic aeroelastic system on which, if you wish, you can attach a flap. And then you have a typical aeroservoelastic system. So what I'm saying today, I will do a bunch of assumptions. The first is that we have 2 degrees of freedom. We normally refer to those as planche and pitch. The second is that it will be a 2-dimensional aerodynamic problem, which we refer to as airfoil in the aerodynamics community. And third is that the elastic restoring forces will be linear in first approximation, which is what you see in most cases anyway. Then there will be mass, the mass of the system, which again will be a rigid body. And then we can say that this is an airfoil of, say, a unit span. So by doing this, I have defined the 3 elements in aeroelasticity. I have aerodynamic forces, I have elastic forces, and I have inertia forces, and all of them interacting on that very simple construction to give me some idea of performance. Now, I need an aerodynamic model. So you guys know about the springs, you know about masses, but maybe not everyone knows about dynamic. So for a start, the way to start on aerodynamics, and this is how engineering went about through the years, you will go to a wind tunnel, you will take airfoils, and what people did for many years is to try every possible airfoil they could think of, this is before CFD, assess the performance and see which ones perform better in better conditions. And that's how wind design happened through many, many years. So a typical scenario is what I'm putting here. This is pulled out from this book by Abbott. It's a classic, 1940, which basically has tons and tons of charts of what happens to airfoils. Very good news of aerodynamic performance is if you plot angle of attack against a normalized lift, a normalized is lift divided by dynamic pressure, 1/2 rho v squared, and the chord, which is as a normalization parameter. What you obtain is straight lines through a very large range of angles of attack. Okay, this is very good news for design. That allows you to do a lot with very little information. So then when you keep increasing the angle of attack, as you have probably heard, you get into something called a stall, in which the airfoil decreases performance, and at some point you don't achieve anything out of them. So most aircraft and most wind blades are designed to operate on this regime, and then in some situations you might have to enter that end over there. The second parameter, which is relevant here, is not just the lift, but also the moments that the forces appearing on the airfoil are generating. And this is the second plot here. And good news is that this is nearly a constant line when you compute it the quarter core of the airfoil. That can be shown through numerical analytical analysis on aerodynamic equations. So what we have is a very simple model for aerodynamic performance. First is that all the aerodynamic forces scale with the dynamic pressure, very, very important parameter, anything that has to do with aerodynamics. And they will appear in many events today. The second is that the resultant lift coefficient, CL, goes linearly with the angle of attack and constants. I'm going to call it CL alpha and CL naught. That's the value at 0, and CL alpha will be the slope. The moments are simply a constant, which again is measured for anything we are concerned about right now. So we have a model for aerodynamics, we have a model for springs, and we have a model for inertia. So we can construct equations for the airfoil. The first problem we normally look at here is what we refer to as static aeroelasticity, which is what is the equilibrium condition that an airfoil on springs and the aerodynamic forces achieves. And the way to go about that is you just do an equilibrium of moments on an airfoil. The airfoil held on a spring, which is elastic spring here of constant K alpha. And then, let me see if the mouse works here. And then I will have forces, the lift and the moment applied. For the moment to be constant, we take it at the quarter chord of the airfoil. And then the distance between the two, which is going to be a physical distance. The elastic axis has to do with the construction. The aerodynamic forces has to do with standard shape, so they won't be on the same location. Very rarely they happen to be on the same location. They will have an arm, and I'm going to refer to that arm as E here. So if you were to find the equilibrium equations on that problem, that would be the reaction of the spring, K alpha times theta, theta being the torsional elastic torsion angle, is equal to the moments on the aerodynamic center times the lift and the distance. Now we have a model for the lift and a model for the lift and the moment. We put it in, and what we have is basically the 1/2 rho v square, and then the Cm constant, and the 1/2 rho v square, the E constant, and the CL alpha constant. Okay, the equation of equilibrium simply says how much is the wind deforming. That's my unknown. Well, it will depend on how stiff is the airfoil, but also how much lift you get out of that deformation itself. So a key feature of our elasticity is that the things we don't know appear both on the structural part of the problem and the aerodynamic part of the problem. How you solve this? This is a linear system, so you move everything you don't know to the left, everything you know to the right, and you solve for it. So what you have is an equilibrium equation that determines how much the airfoil is deforming as a function of the flight conditions. So alpha R, I haven't talked about it. This is the rigid airfoil. This is where you position your airfoil physically. So it's a known constant. Theta is how much is deforming on top of it. That's the one you need to solve for. And everything on the left, everything on the right of this equation is known information. So you solve for this and you get the amount of deformation. So something to be seen on the physics of this problem is that this is an equation of the structure of stiffness times rotation equal to forces. Okay, K times theta equal to some forces. The stiffness will have two elements: an element from the structure, K alpha, but an element from the aerodynamics. So the aerodynamic forces act as a stiffness term as far as the deformations are concerned. The forcing is only or uniquely coming from the aerodynamics. And it comes from the aerodynamic elements which are not dependent on the deformation. Altogether gives you basically the amount of deformation. You just solve this equation and then you get theta as a function of the conditions in which you are. What this is saying as well is that as you increase the angle of attack, alpha R, you will increase theta. So you have an amplification effect in terms of the lift that you will get when you are increasing your angle of attack. It doesn't go linearly with alpha R anymore, or it goes linearly, but with a different proportionality constant, which depends as well on how much is deformed. In general, these problems are going to be written in this form. So what we have is a stiffness of the structure. Q is going to be the dynamic pressure, 1/2 rho v square. A set of aerodynamic influence coefficients is a matrix of how the aerodynamics affects is affected by the deformations, and then some aerodynamic external forces, which may include, for instance, gravity as well. Okay, so this is the most basic aeroelastic problem. In all of this, I haven't talked about drag, and I think it's important to actually stop and think about it. Why haven't I talked about drag? Well, let me first see how drag looks like. Okay, so I'm having airfoils. I'm talking about airfoils. So I have my lift, I have my moment, and then I have the third force, which is going to be the force along the inflow velocity. You plot the drag as a function of the angle of attack. And again, you use the same normalization. CD will be the drag divided by 1/2 rho v squared, and then a chord component. What you see is that the drag is very small, as you would expect if you have a small angle of attack. That's a proper airfoil design. And then as you increase the angle of attack, you get into this separation ratio. As the lift drops, drag increases, and that always that trade-off, of course. And then the drag takes over the response. You have a black body, which no lift comes out, and only drags comes into place. Good news of this is that this is very small in physical units, but it's also acting on the stiff part of the airfoil. Airfoils, the blades are going to be very stiff on the in-plane dynamics. On this axis, you have a lot of mass, so it's harder to move, and it's easier to move on this axis. So it's a small force on the stiff direction. So very rarely drag actually deforms airfoils. As far as aeroelasticity is concerned, becomes a post-processing element. You don't really need to know much about drag when you're evaluating the equilibrium conditions. However, drag is the one thing which we spend the most time when we're doing aerodynamic design. And the idea is, of course, you want it to be minimized to achieve maximal performance. And in particular, in wind blades and wind turbine blades, the drag is linked directly to the available power because it goes against the thrust which is keeping the blades rotating. So what you need to do is to find the aeroelastic equilibrium and then assess the drag such that you can actually estimate the performance properly on the wind turbine blades. But that gives us a huge advantage in terms of aeroelasticity because drag is by far the hardest thing to compute, but it's the one that in terms of aeroelastic performance has the least effect. So we can get away with simpler methods for aerodynamic design when we're concerned about how wings are deforming, how blades are getting loading on unsteady conditions. All right, so if you're okay with some introduction to static aeroelasticity, then if I will move to dynamic, and probably I can do half of it and then have a quick break, and then the second half. I think I have the most material on this block here. And again, as before, do please stop me and ask questions if anything went too fast or you would like to clarify any detail. I'm going to spend a bit of time now on these problems, so I will to describe it a bit. So I took the previous airfoil. Now I'm making my airfoils very thin, and there is a reason for it, which is it gives me a very simple aerodynamic theory. So what you see, this black line here is going to be an airfoil which is so thin that I can see just a line in space. I put in a flap, so I want to deal with control issues associated to it. And as before, I'm going to put that airfoil on two springs, one spring for vertical displacements on the plunge degree of freedom, and 1 degree on the torsional displacements for the pitch degree of freedom. I will have equally a mass now because I'm going to consider this point on the situation in which I have motions, dynamics of this system. And that mass will go around a center of gravity, which I'm going to position somewhere else on the airfoil. So in dynamic aeroelasticity, I will always need to deal with first identification of aerodynamic effects, lift, and moment. And again, these will be forces which apply at a particular location of the airfoil as a resultant forces. I will need to deal with elastic effects, the torsional springs, KH and K alpha, which again will be applied at a second location, X, EA, I put that notation there. And then I will have a third effect, which is inertia, which will be applied at a third location. And then if I have a flap, the flap will be defined by its own size. So I have a fourth location point on the airfoil. Okay, all these will depend on the design, but all these are key drivers on the performance on the airfoil, on the aeroelastic performance. So I have that basic system. I'm going to define 2 degrees of freedom for it. So H being the vertical displacements, alpha being the torsional displacements, and beta is going to be my command. So this is not a degree of freedom, it's known control inputs, whatever we want to do with this flap. This airfoil, as the previous one, is going to be on a current. So a stream, velocity 1/2, or dynamic pressure 1/2 rho v squared. And then if I wanted to compute forces, what I will need to do is to link the forces to the distribution of pressures that appear on the airfoil. So typically, if you took an airfoil and you look at what's going on top of the airfoil, you will see something that looks like this. This is the distribution of pressure. Normalized CP means the pressure on the airfoil divided by, again, 1/2 rho v squared is the key magnitude that appears everywhere. And what this is saying is that I will have a distribution of pressures associated to the particular angle of attack and the flow conditions in which I am. I define delta as the pressure on the upper side minus the pressure on the lower side of the airfoil, which typically is what it will happen. So you have another pressure field applied there, which will be pulling typically in that direction. Actually, they're both pulling in the right direction. And then what I will do is integrate those pressures to obtain the lift, or integrate those pressures times a distance to the reference point to obtain those moments. Okay, those are the ones I said before we obtain empirically. What I will need very soon, I will need models to compute those. So once I have that, the next thing I will do is to say, well, what are the equations of equilibrium? And you can use any of the methods that you have to your disposal. Since this is a very simple system, I like to just compute this through a free body diagram. So you have all the equilibrium of forces and moments on a system which is basically subjected to the lift and the moment, the reaction forces from the springs, and the inertia forces on the center of gravity. You add all those forces together and write it in terms of h and alpha and its derivatives. What you obtain is the classical mass times classical mass times acceleration times stiffness times displacements equal to the applied forces. What applied forces, again, are the lift and the moment on this problem. So this is the second order differential equation that describes the dynamics of an airfoil on springs. The one thing which becomes tricky here is what's going on the right-hand side of the equation, the dynamic forces. When the airfoil moves and displaces, is not just anymore that the lift is proportional to the angle of attack. We enter the domain of unstable dynamics, and that's the one thing that requires a little bit of attention. So what I like to do next is to basically go a quick summary of what things actually we need to consider when we are computing unstable dynamics on airfoils. So the starting point, this is a fluid. The starting point is going to be Navier-Stokes equations. That's always the way you start when you're doing analysis of flows. I only put here two of them. There are three equations, or five, depending on how you count them. The equation of conservation of mass, which basically links how density changes. This is the first equation here. How density changes as you move on the fluid. This is necessary for compressible flows in which the density may change on different locations. Basically goes the total derivative move with the gradient of the velocities. That's fundamentally the dependency you see there. We have the second equation, which basically gives you the conservation of momentum around the flow. And basically this is Newton's law applied to flows. What it says is that the mass times acceleration, that's the first equation, is driven by the pressure gradient of the pressures that appear. There's a pressure gradient and the viscous terms. Yeah, Borjan?
Yes, so I have another question. Do you have to assume compressible flow? Do you must have an equation for the density?
No, that's what I'm going to do next.
Okay.
So what I'm going to do is I'm going to make the flow incompressible. Thank you, Borjan. So, and this is because wind turbines are designed such that they work at lower speeds. However, it's not that trivial, okay? So you think about a wind turbine, the maximum speed is achieved at the wind tip. At the wind tip, it goes as the angular velocity times the radius of the wind turbine, and these wind turbines are becoming very large and spinning at a reasonably large speed. So this is a design constraint. Typically, is referred to the tip speed ratio. For wind turbines, that maximum speed is peaked to be around 0.3, max 0.3, which is the lower end of incompressible assumptions. Okay, and this is effectively a design choice. It's easier to basically design wind turbines under those conditions, so they become they perform under incompressible flow conditions. Incompressible means density is constant, and density constant means the first equation becomes the gradient of velocity equal to 0, which is an algebraic equation as opposed to a differential equation. It changes the essence of the problem to solve. The second assumption we'll do, and again, this is relevant for the problems we have in mind, is that the viscous terms that appear on the mass, and the momentum equation are dominant on the boundary layer. And this is when you look into the physics of this problem, they become the most important when you have you're looking very near the walls of the body. They drive mostly the drag, but then, as I said a while ago, drag is not something we are particularly concerned about. To obtain lift, fundamentally, we need to be able to estimate the pressure-driven forces, and those are not that much dependent from the viscous terms. And if I recall, Julia saw some plot in which he was precisely looking into canceling these terms in and out and evaluation of the forces as a way of demonstrating that this typically is the case. So because we are concerned about lift, then we can do the second assumption, which is assuming that the flows are invisible, and that's essential for anything we do. If you have invisible flows, you need to solve field equations. You need to deal with the full Navier-Stokes equations. As soon as you make flows invisible, that allows you to basically do potential flow theory, which is a different order of magnitude on complexity. Borjan, you left your hand out. If you want, or at least you had another question.
Sorry.
No problem. So second assumption is we made the flow invisible, which means we're going to get rid of the viscous terms on the momentum equation. The third assumption has to be with the features of the flow in which we operate. So we are going to be dealing with incoming flows which basically are homogeneous, so coming with a constant velocity. And that defines that those flows will be rotational at source. Then because of the assumption we made above, we can, or we do expect that those flows now become irrotational everywhere. And that implies that the curl of the velocity, or the cross with the gradient, becomes to 0. The vorticity everywhere on the flow can be make exactly equal to 0. On those three conditions, from the third condition, then we have that the velocities can be derived as the gradient of potential flow function. From the first equation, now we have that the gradient of the divergence of the gradient becomes 0, which becomes the Laplacian of the potential flow functions is equal to 0. So potential flows basically reduce the full Navier-Stokes equations into a very nice simple PD, a linear PD on the potential flow function, which is Laplace's equation on the potential flow. It's an elliptic equation. It has very different features in terms of when you solve the problem numerically, and the key one being, of course, is much easier to solve. Now, this is a stationary function, so there are no time dependencies, yet my airfoils are moving. So there is a third element to the problem, which is this is on an airfoil, and what I put here is a cartoon of how the airfoil looks like with arbitrary deformation. So this line here, I refer to those as a flying carpet. This is an airfoil which is deforming in an arbitrary way, and this psi is the local position of the airfoil as you move along this axis. So what you have in those cases is a flow which is driven by the potential flow equation, the Laplace's equation of the velocity field, or the velocity potential. But then we need to satisfy the conditions that this flow is going at a constant speed upstream, that when the flow reaches the airfoil, it cannot go through the airfoil. That becomes a boundary condition on the equation. And this is basically, you write it in terms of the relative velocity between the velocity, the flow velocity, and the solid velocity projected onto the local normal is equal to 0. The flow cannot go through the airfoil. Doesn't say anything about the tangential velocity, which can be anything. To fix the tangential velocity, we will need to go into viscous effects, which are the ones we're neglecting. So we cannot say anything. This is called a slip condition on the flow. And then to close the problem, what we will have, and this is a fundamental feature of airfoil aerodynamics, is that you have two different flows going on top and bottom of the airfoil as you go down the airfoil, which don't talk to each other. So when they meet at the end, they need to but they will meet at different speeds in terms of tangential speed. You should expect that to happen. So what we have is a discontinuity which is not accepted by the potential flow equation. So what is done there is to basically open the domain to allow for this, or to make the domain to work all the way to the discontinuity on both directions, but make the discontinuity itself not part of the domain in which we solve the equations, and then enforce this as an additional boundary condition. This boundary condition will be coming from the physics of the problem. The physics is whatever is going on there, this is going to have the same pressure to be in equilibrium on top and bottom of that wake. So we refer to this as the wake. It is possibly the most complicated bit to analyze on anything that has to do with aerodynamics. And in the simplest model, what we're dealing with here, the wake is going to be defined simply as a zero jump of pressures by assumptions on linearity on a line. I'm assuming this myself now, a line that basically goes along the string from the leading edge to the airfoil to infinity, but never moves from the horizontal plane. In reality, these may oscillate and be quite complex. This is a first order approximation to the problem. Okay, let me put this in some more detail here. So what we have is this problem here, which is the potential flow problem on a thin airfoil. Okay, everything very small, so linear assumptions. Therefore, the velocities on the flow on the flow are going to be written in terms of a perturbation around the mean flow velocity, B infinity times a small perturbation in U and a small perturbation in W. Yes, Pietro.
Yeah, could you please explain again, because I didn't really get it, how it's handled the discontinuity at the end? So you said that there is a problem of discontinuity at the end because there are two different tangential velocity. So what you do is that you open the domain there. Yeah, but I didn't really get it into details.
So basically, the domain in which we are solving looks like this. Okay.
Yeah.
And these here, the Laplace's equation are working, and they don't.
Okay.
Now this becomes boundary conditions. What we do here is to do this pressure jump, and what we do here is to enforce the non-penetrating boundary condition. In the assumption that we have here, my domain is much simpler. My domain looks like a straight line, and this, because my airfoil is infinitesimally thin. Okay.
Yeah.
And that's about it. Now we solve. Basically, we need to add an additional boundary condition to that domain, which is on that wake that we are introducing.
Okay. Yeah. So it's somehow a workaround to not have to impose your equation in that part because they're not working there. Absolutely. So somehow you take it out of your business. But it makes sense physically because there they don't work, right? I mean, there you can do that, those assumptions.
Shear layer is driven by viscosity. So, it's consistent with the assumptions we took at the beginning. We either solve the viscous time. When you don't have any Stokes solutions in CFD, you don't just make a hole there. You model the whole thing, and the viscous times take care of the wake. Indeed, the wake doesn't become infinitesimal anymore. It has thickness, and everyone that has seen a CFD plot, you see that actually you have a trailing edge kind of driven wake, which is substantial. It's typically the thickness of the airfoil once you go a few cores downstream. Now, because we are doing all these potential flow assumptions, we can get away with this model. And again, it's an excellent model for what we care about, which is driven the lift, lift-driven problem. So it will be terrible for drag, but that's not what we're after.
Okay, thank you.
No problem. So again, I'm solving this as a linear problem, which means I'm going to look at the perturbation on the velocity U and W, and then the boundary conditions I talked about, the conditions on the wake, differential equations. I just put all this together basically to put some names. So these things have some names. These in aerodynamics is called the non-penetrating boundary condition. This condition is called the Kuta condition, and this, well, is the Farfield condition, a more generic kind of name. Now, just to put some details on that, the norm is going to be the sine and cosine of the tangential vector defined by psi as you move along x. In first approximation, when these angles are very small, that's going to go as basically minus the derivative, which is the slope, and one of the other axes. And the velocity of the solid on this very simple approximation is simply the velocity in terms of the derivative of xi with the vertical component. So you put those into the non-penetrating boundary condition, and I would go through the algebra, but it's very easy to show that then what that gives you in the linear approximation is that the vertical velocity of the flow on top of the airfoil has two components. One, which is driven by the slope, there's the angle of attack effect, velocity times the slope at which it has to slide down as you go down the airfoil. The second is the actual vertical motions of the airfoil itself. Okay, so the boundary conditions are going to be on top of the airfoil and going to be on the vertical velocity equal to the combination of those two effects. There are no boundary conditions on the horizontal velocity on the airfoil because you're allowed to have different velocities on top and bottom and non-zero on the slip flow, potential flow. So we have the boundary condition. Now what we do, because this is an elliptic equation on a Laplacian, is to solve through a boundary element. And I was thinking about putting the equations for that, but actually Mark showed them on Wednesday or Thursday last week. Basically, you use Green theorem on the Laplace's equation, and that allows you to solve not on the field but on the boundary, and then you identify a particular kernel that you like to be able to reproduce the problem. So I will skip that process, but effectively, what you end up in potential flows is instead of having to solve everyone in the domain, you only need to solve on the boundaries and define your elementary solutions for the potential flow equations there. The elementary solutions which are typically used on these thinner flow problems are circulation or vorticity solutions. Now, a vortex, let me see if this works here. Just to give you a feeling what it does, what we do, that should work. So what we do is to basically take solutions of this form. We take flow fields defined as rotational flow fields around a point of this is what I call gamma. My screen's a bit broken on that corner there. And what this defines is velocities which go a tangent to this rotational flow with a velocity vector equal to the distance divided by 2 pi r. And what we do is to superimpose multiple of those on the boundaries. Okay, this is a basic vortex which defines a circulatory or rotational flow around a point. So what we do in a potential flow equation solution is to basically replace the airfoil by the combination unwide, that's a horrible name, a combination of multiple of those that go from the leading edge to all the way to infinity downstream. Andy, I saw your hand. You meant to say something?
No, it's a mistake. Sorry.
No problem.
Carry on.
You see, I'm a very interactive lecturer, as you can see.
I can't believe you noticed. I thought.
No, I'm looking at that screen. No, I set up the screen such that this is in the middle of it. So when someone raises their hand, I see it. Okay, so you guys know.
Yeah, carry on.
Okay. So what we do then is to basically superimpose the singularity solutions all the way, and of course this becomes an unknown. So the problem becomes, what is the distribution of circulation that I will put, or vorticity that I put all the way through my boundaries, such that the flow that they generate satisfy the Laplace equation by choice, they do, and second, the boundary conditions. We don't need to do anything at infinity because the choice of circulation that goes with the distance means at infinity that velocity goes to 0, and then you just superimpose the constant flow speed that goes from the inflow. So that one is automatically satisfied by this choice. So once we have that, then what we do is to superimpose that gamma divided with 2 pi r, and when you look at the signs of the forces, when the x is positive, that's a negative velocity. So the velocity that the flow is seeing, that's what we defined before on the airfoil, is equal to the velocity induced by that distribution of singularities. And that becomes a very simple equation to solve. It's an integral equation in which we need to solve for gamma. There's a problem though. When you write the problem this way, you have boundary conditions on the airfoil, which are these ones here, but you have unknowns on the airfoil and the wake. I separated them here. This is the interval between 0 and C, 0 being here and C being the chord, and the interval between C and infinity being a second interval on the distribution of circulation on the wake. On the wake, we have a second boundary condition, delta P equal to 0, which we also need to enforce to be able to solve this problem. And that one requires a bit more thinking because that still we don't have a way to link velocities and pressures. For that, what we need to do, one thing I should say is that if the flow is assumed to be quasi-steady, which means stationary flows are on airfoils, the circulation on the wake goes to 0, and then we don't need to do anything. But we are concerned about situations in which things are moving, and that means actually we need to solve simultaneously for the bound vorticity, that's the B there, and the wave vorticity, that's the gamma W. So what we have is fundamentally this equation first. That's the condition on the non-penetrating on the airfoil. Second, you have the pressure wake, the no pressure jump on the wake. And third, well, we need something to link pressure and velocity. This is achieved from the equation we haven't used from Navier-Stokes, which is the momentum equation. If you take momentum equation and integrate it on straight lines, and again, this is something very easy to find, so I won't go through details. What you obtain is what is referred to Bernoulli's equation. Bernoulli's equation is an integral of the momentum equation that says that the change on pressure goes proportional to the change on velocity square. And by the way, the reason I keep talking about dynamic pressure, 1/2 rho v square, is because of that. Anything that has to do with airfoils is exchanging pressure by dynamic pressure as you go on the airfoil. And that means dynamic pressure is the key driver in terms of generating forces on aerodynamics. Because we have still an steadiness on the problem, we have an additional term coming out of the integration of the Navier-Stokes equation, which is the derivative of the velocity potential, which also comes onto the equation. And what that says, as you go down the streamline, this, just to be correct, that should be infinity. We have this total pressure upstream, and as we go down the airfoil, that magnitude gets conserved. This is P infinity plus 1/2 rho v square. And then anywhere on the airfoil that you go, you have a pressure which goes as proportional to how much the flow is accelerating. So what is the change of velocity? And indeed an acceleration term, which is how the velocity changes with time. Now, what we need to do is basically do a bit of manipulation on this Bernoulli's equation to be able to link the pressures to the vorticity. And once we have that, then we can close the problem. So I put a bit of algebra here. I don't want to run through all the steps. So basically what we'll do is to do Bernoulli's equation around the discontinuity that we define in our flow. If I have my previous circle that I brought before, and I have that problem there, as I said. So what I say is I'm defining this boundary condition here between top and bottom. I'm going to define the upper part and the lower part of that discontinuity. And I'm going to look at the change on the pressure. Delta P becomes pressure on the upper minus pressure on the lower. And then I look at Bernoulli's equation to see how this changes between the two. So the change of pressures is going to be linked to the change of velocities. That's the first term on Bernoulli's equation, and the change on the potential flow, the velocity potential, which is the second term of the equation. The first term can be written in terms of sum times the difference, and then we look into linear approximations of this equation. This becomes 2 times the velocity plus something which is very small, and this becomes the jump of velocity, which is only linear on the direction in which the velocity is preserved. So this term gives you something that looks like velocity times u, so delta phi times delta x. This is equal to delta u, the horizontal component of the velocity perturbation. And the second term is simply rho times the the change of the jump in the velocity potential between the top and the bottom. So we have a relation between the pressure and the velocity potential. That's the first equation here. Second, this depends on u, but now u can be written because it's driven by the presence of this distribution of singularities. So when we go very close to the axis, we can actually compute the integral that defines the velocity in terms of gamma. And as you get very, very close to gamma, the only effect that is retained is the local one, because that becomes a singularity, everything else goes away. So in that case, that can be very easily seen by doing a bit of algebra on the potential flow equations, that the velocity is equal to half of the value of the local circulation. When you look at the jump of velocities, that becomes twice the jump. So that basically links the local distribution of circulation, of vorticity gamma, to the jump of the horizontal component of the velocity, which we write in terms of the derivative of the velocity potential in terms of x. Okay, so at that point, then what we have is a link between delta phi and gamma, which then we can introduce back into the pressure equation to have a relation between the pressure and the circulation of the vorticity in gamma. In particular, if we do this on the wake, in which we know delta p is equal to 0, and then we integrate, we substitute delta phi divided delta gamma in terms of gamma, and we take derivatives on that equation. So we take derivative with respect to x of the equation in the star. That gives you a very nice clean solution in terms of how the wake vorticity has to evolve with time. And this becomes a convection equation. What this condition is effectively saying is that the circulation that we see on the wake is moving alongside the axis, conserving itself as it propagates. That's a conservation on a convective equation. And that's a very useful solution to have. Okay, what that tells us is how much is gamma w based on how was somewhere upstream. In terms of the physics of the problem, wake becomes a history of past change of circulation that happened on the airfoil. Every time you shed circulation from the airfoil, gets convecting downstream from on the wake, and that information is preserved by the potential flow assumptions. So we have then solved the wake. We have a differential equation that tells us what's going on in the wake. And now we go back with that relation we had before between delta P and delta gamma, and we can obtain the pressures. So since we wrote gamma in terms of the derivative of phi with respect to x, then what we can do is to replace those into that equation there. So the first equation, or the second term on the equation, I don't know why I changed the order, gives you that the local pressure is equal to the local circulation. It's proportional to the local circulation scaled by the velocity. It's a classical solution again of potential flows, stationary potential flows in general. But then you have another term, which is because we have the dependency on the acceleration of the flow. When you integrate that one along x, it gives you a dependency which becomes an integral equation on the change of circulation through the airfoil. In terms of the physics, these will refer to as circulatory effects. This is the basic effect that drives the generation of lift on airfoils. What we have there is that if you have circulation, you have lift, you have acceleration of the flow, and they are directly proportional to each other. The second term, what it says, is that what we have is an additional term associated to the inertia of the flow which is moving. That's what we refer to as apparent mass. It's linked to the velocity of the acceleration of the flow. Acceleration generates a resultant force on Newton's momentum equation. And that one cascades into a pressure field which is proportional to the rate of change in time of that circulation. These we call circulatory effects. These we call apparent mass or added mass effects. We have closed the problem. So we have now a differential equation, an integral equation that solves gamma b, a differential equation that solves the propagation of vorticity along the wake, and then the combination of the two that gives us the pressure on the airfoil. Once we have the pressure of the airfoil, we go back to the definition of lift and moment, and then we can have the lift and moment in terms of the velocity that we have on the free stream and the distributions on bound vorticity on the airfoil. And that's probably, let me put this example, and that probably is a point to have a quick stop. So this problem, by the way, so the problem of generating or computing the lift and the moment can be solved numerically. So that's what Arturo was referring to the other day, we normally use for this in 3 dimensionals what we refer to the unsteady vortex lattice methods. We discretize that distribution of circulation on the wing and the wake. We integrate all these pressure forces. We compute the propagation of circulation as you round down the wake, and that can be numerically written with not too much complexity. And then we obtain those time domain evolutions of aerodynamic forces. Under the assumptions that I'm talking about here, that everything is linear and everything is small, there are closed form solutions for these problems. So you can, and those solutions appear when you move from time domain to frequency domain. So I won't be covering those, but so you guys know about these, the classical solution for that problem is due to Thorsen. This is 1935. Anyone interested in this? It's a beautiful paper in terms of the maths that he uses. And what it solves is the forces on an airfoil, which is moving on harmonic speeds, on harmonic motions on the pitch angle of attack. Okay, so you have alpha equal to alpha naught times sun sine. And then what Thorsen found is that the lift is also harmonic, as you would expect, with a phase delay, phi, and an amplitude change, z. And both of those are linked directly to the frequency vibrations. And he found closed form expressions for both the amplitude and phase of the changes. How those look like? Well, for those, actually, we need to normalize the angular velocity. It uses a normalization in terms of the convective time scales of the flow, so velocity divided by chord. In aeroelasticity, this is known as reduced frequency. And what we do is to say, if you define the reduced frequency, then the CL in frequency domain is going to be the constants on that problem, 2 pi times alpha naught times a function. And the function is called the Thorsen's function, C of k. It has that shape function there, which is these are Bessel functions of the second kind, very easy to code. So it's a problem that actually has a very, very simple analytical solution. Physically, what it means when you have a system that has phase delays and amplitude delays means if you were to plot lift versus angle of attack on an airfoil as I defined at the beginning, and a steady airfoil, you have a straight line when you normalize things by 2 pi. There's a constant that appears on airfoil theory. That a straight line that goes there will start to have the shape of an ellipse when you start looking into phase delays. And then it will be moving down when you start looking at amplitude delays. So what anesthesiodynamics actually produces is moving from this straight line between lift and alpha to these ellipses with lower slope when you have harmonic motions. And at this point, if you guys want, we can have a